So DIFI, the Universal Language for Streaming Digitized RF. So the goal of DIFI is to create wide adoption of an interoperable digital IF standard. So right now, one of the most popular standards out there is VITA 49. DIFI is a specification within VITA 49.2 that is focused on creating three different types of packets, signal data packets, and two different types of context packets, with the goal that we'll be able to, as a community, be able to create different RF devices that are easily interoperable with digital streams. So standards without interoperability, for any of you that have ever used standards like DVB-S2X or VITA 49, different vendors look at specs and implement specs in their own unique ways, and you end up getting a mess of essentially implementations of specs or DVB-S2X or pretty much anything. Over time, this creates a vendor lock-in because now you're stuck with this specific implementation created by a specific vendor. DIFI seeks to break vendor lock-in. So why a subset of VITA, of the VITA specification? So there are two big common digital transport mechanisms today. It's VITA 49 and eCPRI. eCPRI is found in 5G. Of the two, the most widely deployed one within the satellite market is VITA 49. So it makes sense to leverage the great work already done with the VITA 49 standard and make it more defined in a way that creates interoperability between different customers. So some common protocols, we have eCPRI, which we mentioned. It's widely vetted in 5G, which is a big plus. Features remote streaming from radio units to baseband units. There's flow control in it by default. And there's an MNC plane already attached to the standard, which makes monitoring control far easier than with many other methods. The con is it's only used in 5G, so it's not widely used in fields outside of 5G. For everybody in this audience, I'm sure everybody's familiar with ZMQ. ZMQ has an API for development. It features remote streaming. You could actually do flow control when you use ZMQ at the lower level. The higher level of ZMQ is just fire and forget. And it's really efficient. Cons with it is it's not widely adopted outside of like niche communities like our own. And there's no context or MNC attached with ZMQ, so you have to kind of make a layer around that. And then there's UHD Cheddar, which many of us are also familiar with. There's an API for development there, features remote streaming. You could enable flow control with a flag. And then the cons is that Cheddar isn't widely adopted, but there is a DIFI RF knock block available at our GitHub. So thank you for that. The DIFI packet protocol, as mentioned, it's three main packets right now. One is a signal data packet that carries the IQ of the stream. There is where all the IQ data is stored. There's the signal context packet that carries the RF parameters of the stream. And that's where you would get things like center frequency, bandwidth, and all the things that we care about in regards to the stream. And then there's the version context packet that tells you this is the version of the standard that I'm implementing, as standards do evolve over time. And there's timing information within the version context packet. So you could actually get timestamps. So the context packets right now are informational, but they do allow you to create a monitoring control if you so wish in band by using the context packets. So here's what it looks like. There is an Ethernet frame payload, an IP payload. Within that, there's a UDP payload. And within that, you could get a signal data payload, single context packet, or version context packet. So some use cases. So when you have a digitizer, you create a DIFI producer, which is essentially an IQ stream with a context packet attached to it. And then your modem can act as a DIFI consumer. That data is, that IQ stream is demodulated and sent to the cloud if your modem is running at the edge, or you could do this in the cloud if your modem is running in the cloud. So some popular implementations of this are found by companies like Kratos. They currently have a modem that does this. On the other end, the modem produces a DIFI producer, and the digitizer acts as a consumer, and that goes out into the world as RF. Now, there's many more applications for DIFI streams that are outside of the communications market. So for example, you could have a DIFI stream going into a channelizer, and that channelizer now sub-channelizes into multiple DIFI streams. You could have a DIFI stream going into a DSP function that essentially does anything with it. It could create RF, or it could translate to a different protocol that you may want if you're using something more bespoke on your end. Or it could take something more bespoke and turn it into a more interoperable layer like DIFI through a DSP function. So as with any protocol, you can convert back and forth. Some existing tooling that's found on our GitHub, there is a DIFI Python validator that was released by Kratos. You could create context packets, you could create data packets, and you could interact with these packets with the different Python files on the repo. There's a GNU Radio out of tree block called GRDIFI. This was released by Microsoft, and that right now is using data packet sorts and sync blocks, so you could actually interact with data packets in your flow graphs. And there's a DIFI Wireshark dissector that allows you to inspect DIFI packets within the context of Wireshark, which most people are familiar with. And that was released by Joanna Rivera, who works at Microsoft as well. So GRDIFI allows users to communicate with DIFI devices by streaming and receiving DIFI signal data packets within a GNU Radio flow graph. You could also get SIGMF or any other binary file and turn it into a DIFI-compatible stream. So here what you see is the GRDIFI example that is self-contained. You have a signal source that's randomized, you have a throttle, it goes to a DIFI sync, and then you have a DIFI source that goes into a time visualizer. So this is right now running on a VM on Azure, and then splitting the two, you could play around with DIFI packets running from one VM to another VM. This example is also being run on Azure, but you could run this in whatever infrastructure you would like. So this shows the reality that the blocks do exist and they're moving IQ data from one end to another. Combining SIGMF with DIFI has some advantages. So as some of you know, SIGMF is used to share recordings of IQ binary data with a standard metadata format. DIFI being an engine for real-time streaming, you could use DIFI to move data from A to B and then capture that with SIGMF for offline recording and analysis. So here's an example of an SDR. You have multiple DIFI streams. They go to different signal processing modules that then create SIGMF syncs. Or you could get SIGMF sources, run signal processing on it, and stream the data out as a DIFI-compatible stream for use elsewhere. So some trends in RF in the cloud and why we're caring more as a community about digital transport. So the traditional way of doing SATCOM is you have a device, it's sitting at some gateway or it's sitting at some remote station, and it's interacting with your RF chain. Happy trails, it works. But if you wanted more flexibility in terms of how you could load different waveforms or how you could leverage the cloud to do added value in terms of signal analysis, you kind of need to now think about moving that RF out to the cloud and doing different functions in the cloud. DIFI enables this by allowing you to move from the edge to the cloud in a way that's standardized, but this has very quickly shown its inefficiencies in terms of the amount of data you have to go from the edge to the cloud when you're moving IQ. As many of you know, when you start doing the math, if you're doing 16 bits and you're moving IQ, it adds up real quick. So the trends are now creating elasticity brought to you by the cloud to the edge by using DIFI at the edge to move data within your edge network and demodulating the data at the edge with the same flexibility that you would any other software-defined radio. So it's nice in the sense that you can now create transport locally, but if you wanted the option to move the transport to the cloud for further analysis, you could. So it gives you a lot of diversity in what you could do. Some current members within DIFI, we have government members, we have commercial members. These commercial members, everything from RF devices to cloud providers to antenna makers, you name it, they're involved. So it's a rather big group of people that are essentially supporting the standard and evolving the standard. So how to get involved? We would like people that could get involved to help define DIFI features for your RF needs. There are more RF needs than SATCOM in the world. Help create tooling for interacting with DIFI streams and or provide feedback on existing tooling. It'd be great for the community to take the tooling for a spin and provide feedback and really test drive everything that's out there today, incorporate DIFI into a project, and provide feedback on the standard. And then help shape the future of the cloud at the edge, help shape the future of DIFI at the edge and in the cloud in terms of what features or what specs need to get evolved to meet your needs. So as an example, we are currently evaluating the addition of diagnostic packets so you could do closed loop in-band testing. I'm sure there are other ideas out there that would benefit the standard that everybody here could contribute to. So with that, I will open the floor to questions.
All right. Question worthy.
So having recently moved some of our stuff over to the DIFI standard, one of the things I think will be an issue in GNU Radio is it doesn't support CF data, it only supports up to CI. Is that something we're looking into to expand it to be able to support CF as well? Because it only supports up to 16 bits I and Q and literally says in the standard you cannot support float. So, you know, I know it's VITA 49 specific, so it could support it and just has to be expanded to another data type. But I'm just curious, is there a push on that? You know, where does that move in the future?
So currently that's not on the radar, but I'm glad that you brought it up because it is something we could incorporate because the idea is to make GNU Radio an integral part of the testing solution suite for DIFI. So I would take that suggestion. I'll talk to you offline to capture it properly. But yeah, I mean, we want to make sure that this is something everybody can use in a useful manner. Any other questions?
Hey, you mentioned that the DIFI protocol supports 3 different types of packets. You know, signal data is one of them. Does the out of tree module also support the context packets?
No, today the out of tree modules do not support the context packets, but that would be a great addition for the community to do or anybody really that is into this.